Push that rock with Simpson math. Giggle. We're going to talk in this lesson about the derivative. We just got through studying limits. Next, we're going to study derivatives. And last, we will study antiderivatives, also called integrals. And so we are studying three operators in this class: limits, derivatives, and integration, or integrals, or antiderivatives. Those three operators are what we study in calculus. And in this lesson, we're going to get a glimpse at the derivative. And in particular, we're going to be thinking about the derivative at a given point of a function. Now, a derivative is a near synonym for slope. It's not a synonym for slope, but nearly so, because one interpretation of the derivative is the slope of the curve at a given point. Now, I've started here with a line because lines have this key feature. They always have the same slope, and this particular line always has a slope of 2. So the key feature of this line is the slope is always 2. And the derivative will give us the slope of a function at any given point. And since this, when I say point, I mean on the x-axis. So at this point 1, it has a slope of 2. At this point 2, it has a slope of 2. At this point a half, it has a slope of 2. So the derivative should give us 2 because the slope is 2. Now I want to talk about the notations because they get confusing fast. We have multiple notations. Just get used to the fact that there's multiple notations. Euler invented two notations. One was this capital D, subscript x, letting us know it's the derivative with respect to x, in case there's more than one variable. And so you put the function here, and that means take the derivative of that function. Well, the derivative of this function is 2 because the slope is always 2. Another notation that Euler invented was this prime symbol, y prime. You read this as y prime, or the derivative of y. And the derivative of y is 2 if y is equal to 2x plus 1. Now Leibniz used this notation, and we're going to discuss later in the course why this notation, while not as handy, not as quickly written, is genius. We'll talk about that later. But this notation, dy dx, is another notation for the derivative of y with respect to x, much like this is the derivative of this with respect to x. Now, again, if y is 2x plus 1, then the derivative of y with respect to x is 2. Now, I said the derivative is slope, so you're getting a glimpse of the genius of this notation because you already see dy is in the difference in y over dx is in the difference of x. In fact, we call this the differential of y and the differential of x. So if the derivative yields slope at a given point, that's what it does. But see, curves, they have the key feature of not having the same slope all the time. So how are we going to get the slope at a given point when it takes 2 points to calculate its slope? See, I can get the slope of this line because I have 2 points. But getting the slope of the curve, if I use this line to get the slope of the curve, well, clearly this line is not the slope of the curve here or here. Maybe somewhere in here, and later we'll learn there's one place in here that will have the same, at least one place in here that has the same slope as this line, but not there. The slope seems flatter. Not here. The slope seems steeper than this line. Now, this type of line that intersects the curve at 2 key points is called a secant line. Secant line. So you might want to put that in your notes. The slope of the secant line gives us the average slope of the f of x over this interval where the 2 key points are. So on this particular example, I put the points at 0 and 1 on the x-axis. So over the interval from 0 to 1, the average slope of the curve would equal the slope of this secant line. But that's not what we want. We don't want the average slope. The derivative doesn't tell us the average slope. It tells us the slope, the steepness of the curve at a given point. We want to know the steepness, the slope of a curve at a given point. How are we going to do that? The answer is limits. That's why we learned limits first. Let's say we want to know how steep the curve is at this point A, for this point A right here. In other words, at that point, A, f of A, on the point on the curve, how steep is this blue curve here? How steep is it right there? And the way you do that is you start getting some secants, like this red secant, and then you get another secant, only, see the red secant, the second point was pretty far away. This purple secant, the second point is closer to A. And you keep doing that. You keep doing it until the second x value collapses down on this x value. Well, you can't actually do it at that x value, but you can find the limit. You can see what slope is it approaching. See, here we have it's kind of flat and it's getting steeper and steeper and steeper and steeper and steeper and steeper and steeper. What slope is it approaching? The limit will equal the slope of the curve. Now, by the way, when you have a line that has the same slope as the curve at a point and intersects the curve at that point, it's called a tangent or a tangent line. So a tangent is a line that shares a point and a slope with the function. When you compute a derivative, you're not only getting the slope of the function, you're also getting a slope of that tangent, because the tangent has to have the same slope as the curve. So how do we do that? Well, here's a curve. We start off with some secant line, and we get the rise over the run. We get the slope. We get this rise over run of this secant line. How do you do that? We use the slope formula. Y2 minus y1 over x2 minus x1. The difference in the y's will be the rise. The difference in the x's will be the run. And we're going to use h to represent run. H is in how far away you are from A. How far away that second x value is from A. And if it's far away, well, then this run is big, so h is big. But when it's small, h is small. And remember, we're going to find the limit as this point collapses down on this point on the x-axis. So as the run collapses to 0, so as h goes to 0. That's what we're going to do. Now, to plug into this formula, we find the second y value. Well, that's this point right here, f of a plus h, and we plug in f of a plus h for y sub 2. And then we find the first y value, well, that's f of a, and we put it in for y sub 1. And then we put in a plus h for x sub 2 and a for x sub 1. But wait a minute, if I go a plus h minus a, I'm going to get just h. Oh yeah, that's because what's supposed to be down here is the run, and we just said h is the run. Now, we're going to take the limit of this as h goes to 0. And when we do that, when we take the limit of this expression as h goes to 0, we are computing the derivative of the function when x is a. The slope of the function at the point A. At this point A, we're computing the steepness. Now, remember Euler's notation with the prime? So we frequently use f prime of A equals this. And this, by the way, is the definition of the derivative right here. That's the definition. Put that in your notes. I should have put it in a red box. You're going to use this a lot. Math made simple. It's Simpson Math.